Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on March 12, 2026, exactly 1 week ago. It introduces an incredibly data-efficient approach to training humanoid robots, outperforming prominent baselines by over 40% in success rate across complex tasks using just 800 hours of human video and 30 hours of robot data. The paper is titled Psi-Zero, an open foundation model towards universal humanoid Loco-Manipulation. And, as we'll see a bit later, the way they separate general task learning from specific robot control has some really exciting implications for the future of general-purpose robotics. Alright, Figure 1 shows the end result of this training approach, with the Psi-Zero model powering several humanoid robots in a real-world pantry. The image highlights what the authors call Loco-Manipulation, which means seamlessly combining whole-body movement with complex hand-object interactions. We see the robots handling diverse tasks, like fetching a cup from the coffee machine on the right, pushing a utility cart in the foreground, and wiping down the central table. So, Figure 2 details the staged training pipeline that makes those complex interactions possible. In Stage 1 on the left, a vision language model is pre-trained on human videos to understand general task semantics. Next, Stage 2 introduces an action expert that uses these features alongside real robot data to master precise joint control. Finally, the deployment phase on the right adds a lower body controller with real-time chunking, which helps the robot execute smooth whole-body movements without hesitation. Okay, while the previous figure outlined the overall pipeline, Figure 3 compares the multimodal diffusion transformer architecture used for the action expert against a naive alternative. On the left, this multimodal transformer fuses vision, language, and action representations through a joint attention mechanism, which allows for deeper integration of these different inputs. On the right, the naive approach processes them separately using sequential self and cross-attention layers. The researchers found that this superior feature fusion on the left was essential for translating high-level task semantics into precise joint control. Well, Figure 4 zeroes in on the real-time chunking mechanism, which addresses the latency issues that often cause stop-and-think jitters in large models. The graph tracks a robot joint angle over time to show how consecutive action commands connect. Without real-time chunking, the cyan line diverges significantly from the previous action shown in orange, which leads to jerky and unstable movements. But when this chunking is applied, the pink line aligns much better with the previous trajectory, suppressing that divergence and resulting in smoother control. Next, Figure 5 illustrates the teleoperation setup used to collect real-world robot data. On the left, a human operator uses a VR headset and Manus gloves to capture precise upper body movements, while waist and foot trackers record high-level locomotion commands. This setup cleverly decouples upper body manipulation from lower body stability. Then, on the right, these motions are retargeted to the humanoid robot, ensuring the collection of high-quality trajectories for task-specific fine-tuning. Alright, after Figure 5 detailed the data collection, Figure 7 presents the real-world benchmark results. On the left, the bar chart breaks down success rates across 8 complex long-horizon tasks. Psi-Zero, shown in pink, consistently outperforms prominent baselines like Groot N1.6 and Pi 0.5. Then, on the right, the radar chart aggregates these results by specific skills, highlighting strong performance in maneuvers like grasping, pouring, and walking. Overall, the model achieves an average success rate over 40% higher than the competition, which proves that separating task semantics from robot control is incredibly data efficient. Okay, since the previous figure demonstrated that performance gap, Table 1 breaks down the specific components driving it through an ablation study. At the top, a naive diffusion transformer without any pre-training fails completely. However, introducing the multimodal architecture and human video pre-training boosts the success rate significantly. Finally, adding domain-specific post-training pushes overall success to 9 out of 10, while real-time chunking guarantees that the final execution remains stable. Wrapping up, the big takeaway is that humanoid intelligence scales most effectively by separating general task learning from specific physical control. This efficient approach offers a clear path forward for general-purpose robotics. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.